Welcome to the final session of the IEEE Digital Electronics Problem Solving course. Today we will be covering the chapter problems in chapter 7, Memory and Programmable Logic. I'm not sure if we'll be able to complete all the problems. We'll do as much as we can. Today is the last session. Of course, you all have my email ID, so if you have any doubts, you can contact me through email. Let's get right into it. Problem 7.1. The memory units that follow are specified by the number of words times the number of bits per word. How many address lines and input output data lines are needed in each case? Part A 8K times 16, Part B 2G times 8, Part C 16M times 32, Part D 256K times 64. So the first part gives you the number of address lines that you need. If it's a 8K by 16, that means there are 8K words. For each word you need a different address line. So you need 8 kilo address lines. Sorry, I made a mistake. You need 8 kilo addresses. Now of course you could use 8 kilo address lines, but that seems to be too wasteful. So if you use binary numbers, then you could use a decoder and each address line, each address which in turn is connected to an address line. Alright, you can select an address line by giving a binary input combination instead of selecting the address line directly. What I mean to say is, if you have a few address locations, each with a different address, and an address line pointing to each of those locations, then one way you could do this is, could say you will select this line directly and give 0 to all the other lines if you want to select this. or you could select this line directly by giving a 1 to the second line, or you could select the third line by giving a 1 to the third line, or you could give the fourth line by giving a 1 to the fourth line. But in this case, all four of them are inputs, so you need four input lines. Instead of doing this, doesn't this look very familiar to a type of binary circuit that we have seen? It looks very familiar to the output of a decoder. So instead of doing that, having four select lines, four input lines, I'll have a decoder with two input lines which has four select lines. I'll connect the address lines to one select line each. So now what will happen if I give the binary input combination 0 0, I'm selecting the first address line. If I give the binary input combination 0 1, I'm selecting the second address line. So it will be 1 0 0 0. If I give 0 1, it will be 0 1 0 0. So I'm selecting the second location. If I give 1 0, I'm selecting this location. If I give 1 1, I'm selecting this location. So the number of input lines is smaller, and you can represent a larger number of addresses using a smaller number of bits. So this is a problem at scale where if you had 8,000 address lines, you would need to give inputs directly to 8,000 different address lines. So you need 8,000 switches, right? Or you need to turn on the power supply for turn one of the power supplies on for 8,000 of the lines. You don't need to do that. You can use a M. M is the number of inputs is to 2 power m decoder. A decoder, if it has m inputs, it has 2 power m output lines. And for each input combination, it will select only one of the output lines and give a high to that output line, high voltage level. The rest will be at low voltage. So that means that I need only if 2 power m is equal to, so m address lines can address 2 power m locations via a decoder. So 2 power m is equal to 8k, which is 8 into 1024, which is 2 cube into 2 power 10, which is 2 power 13. So we need m is equal to 13 address lines. That is, you need ceiling of log of the number of addresses to base 2. So in the second case, you need, since all of these are powers of 2, the number of addresses 2 giga is 2 power 30 right? It's giga is 10 power 9, but in binary it's 1024 into 1024 into 1024, so it's 2 power 30. 2 into 2 power 30 is 2 power 31. 31 address lines. Part C, you need 16 mega is 2 power 4 into 2 power 20, 2 power 24, so 24 address lines. Part D, 256 kilo, 2 power 8 into kilo is 2 power 10, 2 power 18, so 18 address lines. And the number of IO lines is equal to number of bits per word. So for each bit you need an output line. So you need 16 here, here you need 8, here you need 64, sorry it's 32. Part D you need 64. Problem 7.2, give the number of bytes stored in the memories listed in problem 7.1. You have in each of them 8k into 16 number of bits, because there are 16 bits per word and there are 8k words, that is, and 1 byte is 8 bits, so you have 8k into 16 divided by 8 is 2k into 16, 32 kilobytes. Part B, 2 giga into 8 by 8 is 2 gigabytes. Part C, 16 mega into 32 by 8 is 64 megabytes. 256k into 64 by 8, 256 is 2 power 8. Out of 64 you can take out 2 square, which will give you 2 power 10, which is another kilo, so it will become a mega. If you take out 2 square, you will get 16 mega bits by 8, just 2 mega bytes. 7.3, word number 563 in the memory shown in figure 7.3 contains the binary equivalent of 1212. List the 10-bit address and the 16-bit memory content of the world. Figure 7.3 just uses the concepts of problem 7.1 and 7.2. I won't draw the figure. There's nothing much in it. It's just asking word number 563 in the memory is shown in figure 7.3. So if it's 563, what is the binary equivalent of that? You have 256, 512, 128, 64, 32, 16, 8, 4, 2, 1, 512 plus 32, 544 plus 16, 560 plus 3. So this is the address, 10-bit address. 16-bit memory content of the word is binary equivalent of 1212. So 1212, what is the binary equivalent? We use the concepts that we learned in the previous chapters to convert a number from decimal to binary. You divide by 2. This is 606 with remainder 0. 303 with remainder 0. 151 with remainder 1. 75 with remainder 1. 37 remainder 1. 18 with remainder 1. 9 with remainder 0. So the 16-bit memory content is that's 4 bits. That's 8, 11, 12, 13, 14, 15, 16. It's just 0 padded to the left. Problem 7.4. Show the memory cycle timing waveforms of the write and read operations. Assume a CPU clock of 150 MHz and memory cycle time of 20 nanoseconds. It's a theoretical question, I won't solve that. 7.5. Write a test bench for the ROM described in example 7.1. The test program stores binary 7 in address 5 and binary 5 in address 7, and the two addresses are read to verify that stored contents. I will not do that either. 7.6. Enclose the 4x4 RAM of figure 7.6 in a block diagram showing all inputs and outputs, assuming 3 state outputs. Construct an 8x8 memory using 4x4 RAM units. Okay, we can do that. Firstly, the 4x4 RAM unit, if you write it as a block diagram, has 4 input lines which are used to write to the RAM, and 4 output lines which are used to read from the RAM, and read write control. An address select line to select which of the two address select lines, and an enable which enables the RAM. To get an 8x8 RAM, you just need to put two 4x4 RAMs in parallel will give you a 4x8 RAM, right? Because this can store 4 bits per word, this can store 4 bits per word. Together they store 8 bits per word. As long as you select store, while storing, you store at the same address locations in both RAMs, and while reading, you read from the same locations in both RAMs. That gives you only 4 address locations. So if you have another pair, that gives you 4 more address locations. So you have 8 address locations, each with 8 bits. Now the first 4 inputs, I2, I3, I1, I2, I3, I4, will be given to the both the top and bottom RAM on the left side, and the remaining 4 inputs, I5, I6, I7, I8, are stored on the right side RAMs. Of course, which RAM it has to be stored in will be selected through a control circuit. Similarly, the outputs First 4 bits of the outputs are from the left side RAM, and the next 4 outputs and which RAM you enable depends on which address line you want to select. So you can that's too clustered. Let me just copy this 4 times. So the same read write is given to all 4. You don't need extra read write inputs. We can just disable those blocks that we don't want to use. And for the address, you can use one more address line A2 and give that to the enable. Now what you do is, if A2 is 0, you select RAM 1 and RAM 2. If A2 is 1, you select RAM 3 and RAM 4. So enable RAM 3 and RAM 4. That means whenever the address says 0 followed by something 0 0 0 0 0 1 0 1 0 or 0 1 1, A2 is 0, so it has selected the top 2 RAMs. So for that you need A2 complement. A2 complement is fed to RAM 1 and RAM 2 A2 is fed to RAM 3 and RAM 4. And that's it. The first part of the RAMs have inputs I1, I2, I3, I4 on the left side, and outputs O1, O2, O3, O4. The RAMs on the right side will write I5, I6, I7, 8, I8, and will read O5, O6, O7, O8. So that's how you get an 8x8 RAM from two 4x4 RAMs. Problem 7.7. So when you are using a decoder to decode to the address lines, a decoder, let's say it has k inputs, then the number of outputs will be 2 power k. To get each output, you need one AND gate. So you need 2 power k AND gates. and each of those AND gates must be an AND gate with k inputs. So the fan in is k. To reduce the size of the decoder that you are using, you can use more decoders but of lesser size. Instead of one decoder with k inputs and 2 power k outputs, you can use several decoders with less than k outputs and less than 2 power k. And you can do it in a two-dimensional selection scheme. So you arrange the memory cells in an array, in a square array. So instead of using a k input decoder, you use two k by 2 input decoders. So one of the decoders will select the rows and the other decoder will select a column. So here what will happen is you have 16k addresses. So 16k addresses, which means log to the base 2 of k is 10 to the power 10 into 2 power 4 to the power 14, which is 14 address lines. We need a 14 is to 2 power 14 decoder. If we arrange all the memory cells in a row, instead of that, if you use it in an array, then we can use a 7 by 2 power 7, which is 128 decoder. The following way, could use a 7 is to 128 decoder to label the rows. That will select the row, and should use another 7 is to 128 decoder and there can be a memory cell at each of the meeting points of the two two lines. Wherever a vertical and a horizontal line meet, you have a memory cell. So each of the memory cell can be identified or located by one row address line and one column address line. So instead of using a single 14 is to 2 power 14 decoder, we are using two 7 is to 2 power 7 decoders. So the number of decoders you use increased, but now each of these decoders you need only 128 AND gates instead of 128 AND gates for the first decoder and 128 AND gates for the second decoder. That is, need 256 AND gates, each with 7 inputs. Earlier you needed 2 power 14, which is 16k, around 16,500 something AND gates, and each one of them had 14 inputs. So this is called coincident decoding. Let's go on to the next problem. Alright, there was one more part left in the previous problem. Part B, determine the X and Y selection lines that are enabled when the input address is the binary equivalent of 6000. The binary equivalent of 6000, you can do it yourself. 6000 base 10 will be equal to 01011 in base 2. So the first 7 bits are used to decode in the Y direction, and the next 7 bits are used to decode in the X direction. So X is 46 base 10, Y is 112 base 10. Alright, we'll go to problem 7.8. How many 32K by 8 RAM chips are needed to provide a memory capacity of 256 kilobytes? 32K by 8 has 32 kilovolts each of 1 byte size. If you need 256 kilo addresses, you need 8. How many address lanes are needed? To select one among 8 RAM chips, you need 3 address lanes to select the RAM chip plus 32K addresses need log to the base 2 of 32K, which is 3 plus 32 is 2 power 5, a kilo is 2 power 10, 2 power 15, 3 plus 15, so 18 address lines, of which the internal address lines, the 32K address lines, are connected to all of the 8 RAM chips. So, of which 15 are connected to all RAM chips. Connected to the address inputs of all RAM chips. Part C is how many lines must be decoded for the chip select inputs. Specify the size of the decoder. For chip select, we need 3 lines. A 3 is to 8 decoder. For addressing within a RAM, we need a, well, they have not asked that, so I guess that's it. Need a 3 is to 8 decoder. Moving on to problem 7.9. A DRAM chip uses two-dimensional address multiplexing. It has 13 common address pins with the row address having one bit more than the column address. What is the capacity of memory? So in address multiplexing, again the memory cells are arranged in a form of an array, but unlike the previous case where you use two different decoders, so two different sets of address lines to address the locations, here you use the same address lines, except that at one time you say now I am giving you the row address lines and give the row address lines, so it will select the row first, then you use the same pins at a different point of time to say that you are giving the column address and give the column address, then it will select the column within the row that has already been selected. So there is a select line for the row address and a select line for the column address. First you will select the row address and load the row address onto the address bus, and that will go and select which row you want to read or write to. Then you disable the row select line, row address select, and enable the column address select, and then you can use the same pins to give the column address. So actually there are two decoders here too. One is the row decoder and the other is the column decoder. So in that sense it is similar to the two-dimensional coincident decoding, but we use the same set of pins to give the inputs to the row decoder and the column decoder. So what you do is you have a row register and a column register. Let's say you have 8 bits of row address and 8 bits for column address. It is 256 row addresses, 256 column addresses. So the total number of addresses is 256 into 256, which is 2 power 60. Okay. Now what you do is you use the same pins in the IC to give the row address, and you use a register to store the row address in the row register first, and then you enable the column select, and then when you enable the column select, so the row register will now not take the inputs provided to the pins, so it will not change its contents. Whatever was already present at the row register earlier will be preserved, but now the column register is enabled, and the address you have put at the pins of the IC, those will be sent to stored into the column register, and then both the row and column registers are disabled. And now from the registers you'll get you'll decode the outputs of the registers using decoders. So it's called multiplexing because you're using the same set of pins to give the address of both the rows and the columns, except that you are using it at different times. So that's multiplexing in the time domain. So what does that mean for our problem? How do you solve problem 7.9? Well, X has there's 13 common address pins. Row address has one bit more than the column address. What is the capacity of memory? Of course, you can use all 13 common address pins first to get the row address. So X is 13 bits, Y is 1 bit less, so it's 12 bits. So 2 power 13 row addresses, 2 power 12 column addresses will mean 2 power 13 into 2 power 12, which is equal to 2 power 25 addresses or address or locations, memory locations. So that gives you the capacity of the memory. Of course, the total memory capacity will also depend on the number of bits that you can store at a memory location. So the size of the word will also decide the capacity of the memory. 7.10, it's a question based on Hamming codes, which is an error correcting code that can correct a single error. So the number of data bits is 8, K is 8. You need Number of coded bits is 13, so you need 5 parity bits. So to get the 8 is to 13 Hamming code, first you get 8 is to 12 Hamming code. Sorry, 8 is not 8 is to 12, 8 12 Hamming code, 12 8 Hamming code, or the 8 12 Hamming code. And then the 13th bit, which is a parity check bit, is the exclusive OR of the other 12 bits, which will produce even parity at the even parity when you consider all 13 bits together. So if there are odd number of ones in the first 12 bits, then P13 will be 1, which will make it an even parity including 13 bit. So the Hamming code itself is 812 Hamming code is this. You have parity 1, parity 2, and the first bit or the third bit of the code, first bit in the message, then parity 4 followed by 3 more bits, parity 8 followed by the last 4 bits. That's a code word where the indices are 1 2 3 4 5 6 7 8 9 10 11 12. P1 is the XOR of bits 3 5 7 9 11, all those bits which have 1 in the twos place, all those indices which have a 1 in the twos place of their binary representation. For example, 1 1 has a 1 in its not twos place, the units place. 1 1 has a unit, a 1 in its units place, 5 7 9 11, that is the odd numbers. So 3 5 7 9 11 4 1, so it's a 0. P2 is the XOR of all those indices, bits with indices that have a 1 in their twos place. So for example, 1 1 and 1 1 0 6, 1 1 1 1 1 is 7, which has 1 in its twos place, 10 1 0 1 0, 11 1 0 1 1, 3 6 7 10 11. So this is 0 XOR 0 XOR 1, XOR 0 XOR 1, which is again 0. P3 is XOR of all those bits whose indices have a 1 in their fourth place, so does not include 3. It's 0 1 1. 1 0 1 has 1 in its fourth place, so 5 is included. 6 7 8 and 12, so it's 1 XOR 0 XOR 1 XOR 1. It's a 1. P4 is the XOR of all those numbers, all those bits with indices with 1 in the 8th place, basically 9 10 11 12, last 4 bits. 1 XOR 0, 0 XOR 1 XOR 1, which is again a 1. So the Hamming 812 Hamming code word is 0 0 0. This is P4, this is P8, 1 1 0 1 1 1 0 1 1. The 813 Hamming code word is, you XOR all these 1 2 3 4 5 6 7, 7 ones, so XOR of all those is a 1 that is included at the end as P30. Point 1 1. Obtain the 15-bit Hamming code word for the 11-bit data word. Okay, the same type of stuff that we did in problem 7.10. You have P1, P2. Third one is the first message bit. 4 you have P4, then 3 more message bits. 5, 6, 7, 8 bit is P8, 9, 10, 11, 12, 13, 14, 15. The rest are all message bits. 100, 10, 0, 1010. Now the parity check bits are different. P1 is again the XOR of those bits whose indices contain a 1 in the ones place. They're all the odd numbers: 3, 5, 7, 9, 11, 13, 15. So they are 1 XOR, 1 XOR, 0 XOR 1, XOR 0, XOR 0, XOR 0, which is a 1. P2 is the XOR of all those bits whose indices have a 1 in their 2's place, which includes 3, 6, 7, 10. We stopped at that point, and 11. We stopped at that point in the previous problem, but now you have even more message bits. 12 does not have a 1 in its 2's place. 13 also doesn't, but 14 does have a 1 in its 2's place, and 15 also has a 1 in its 2's place. This is 1 XOR 0, XOR 0, XOR 0, XOR 0, XOR 1 XOR 0. It's just 1. Sorry, there are two ones in this combination, so it's 0. P4 is the XOR of all those bits whose indices have a 1 in their 4th place. So it starts out at 5, 6, 7, 12, 13, 14, 15. This is 1 XOR 0 XOR 0, XOR 1 XOR 0, XOR 1 XOR 0. This is 1. P8 is the XOR of all those bits whose indices have 1 in their 8th place, so it includes all those numbers from 9 to 15, which is A1. So including these parity bits, you get 1 0 1 1 1 0 0 1 1 0 0 1 0 1 0. I won't do any more of these Hamming code questions. You can learn them in error control coding classes. The way these books, the way it is taught in digital electronics is not nice at all. It's actually extremely, it is not good. If I say my thoughts, I'll get cancelled. If you really want to learn and understand and appreciate Hamming codes, you should take a error control coding course. I think if you can't take them anywhere in any college or university, then you can watch lectures from NPTEL, from either Professor P. Vijay Kumar from IAC or Andrew Tangraj from IIT Madras. They have good courses on the topic. There's also a good course by an MIT professor. It's not as detailed as the other two courses, but it's pretty nice. Can't remember her name, but she is pretty famous. Of course, she teaches at MIT, so alright, enough with the useless drabble. We'll move on to problem 7.15. Using 64 by 8 ROM chips with an enable input, construct a 512 is to using 64 is to 8 ROM chips with an enable input, construct a 512 is to 8 ROM with 8 chips and a decoder. This is exactly the same stuff that we try to do with SRAM and DRAM and whatever RAM cells. So just take it as homework. You have 512 is to 8, 64 is to 8. So you have an 8 RAM chips. You use a 3 is to 8 decoder with 3 lines to select one among the RAM chips, and within the RAM chips you use so for 512 addresses you need 2 power 9 address lines, out of which you can use 3 to select the ROM chip, and once you have selected the ROM chip you can use the remaining six lines to select one among the 64 addresses, because 2 power 64 there are 64 combinations, input combinations. So, and then you can read the output from the selected address. That's the idea of behind the construction. 7.16 ROM chip of 4096 by 8 bits has two chip select inputs and operates from a 5-volt power supply. Okay, I won't do any more ROM questions. There's only about 35 minutes left in the session, and I want to do at least a few questions on PALs and PALAs. So I'll skip to 7.19. 7.19 to 7.29 are all based on PALs, PALAs, etc. We'll try to solve as many of them as we can. Tabulate the PLA programming table for the 4 Boolean functions listed below. Minimize the number of product terms. A of xyz summation 1356, b of xyz summation 0167, c of xyz summation 35, d of xyz summation 12457. So they have already given the sum of min terms expression, boolean expression. You just have to use the k maps to minimize, and you will get a x bar z plus y bar z plus x y z bar. B is x bar y bar plus xy. C is x bar yz plus x y bar z. Now D has 5 min terms, so it will have 5 terms. Instead of that, you can minimize D bar, the complement of that, which has only the 3 min terms, 0, 3, 6, because we need to reduce the number of product terms. So D bar has x bar y bar z bar plus x bar yz plus x y bars x y z bar. Now we will write the PLA programming table. Where we list out the product terms, x bar z, y bar z, x bar y bar. All those terms we encoded in the expression of A, B, C, and D without repetitions. Then we have the inputs. X, Y, and Z. So x bar Z, this product term will be high. X is 0, Z is 1, doesn't depend on Y. Similarly, Y bar Z, 0, 0, X bar Y bar, X, Y, X, Y, Z bar, X bar Y Z, X, Y bar Z, X bar Y bar Z bar. Then we have the outputs. A has these terms. B has those two. C has those two. D has these are all true inputs. Last one D is the complemented two outputs. Sorry, two outputs, and D is the complemented output. That's the PLA programming table. Nothing much. 7.20 says tabulate the truth table for an 8 is to 4 ROM that implements the Boolean functions a of xyz summation of 0346 b of xyz summation of 0147 c of xyz summation of 15 d of xyz summation of 01357 considering now the ROM as a memory and tabulate the truth table considering that the ROM is a memory, and then specify the memory contents at addresses 1 and 4. So you have XYZ as your inputs, A, B, C, D as your outputs. XYZ can have 8 different input combinations. Corresponding to that, A, B, C, D have the following outputs. A is 1 for minterms 1, 3, 5 and 6. So 1, 3, 5, 6, and it's 0 for the rest of the input combinations. B is 1 for 0147. Sorry, 01. It's not 1356. That's a different question. It's 0346. So 0346. B is 0147. C is 15. D is 01357. So now what you do is you use XYZ as the address lines and use a decoder to select one of the addresses, 8 addresses. And in each of those addresses, you store the outputs A, B, C, and D. So it's like a lookup table. You want to know what is the output for the input combination 000, then you go to the address, the memory location addressed by the address 000. There you would have stored 1101. Because it's an 8 is to 4 ROM, you can store 4 bits. First bit gives you the value of A, second bit gives you the value of B, third gives you value of C, and fourth gives you the value of D for the corresponding input combination. For a different combination, a different address is selected, so the outputs are different. In this way, you can store the outputs for all the input combinations using a ROM. It is essentially storing the truth table. We'll go to problem 7.25. The following is a truth table of a 3 input, 4 output combinational circuit. X, Y, Z are the inputs, A, B, C, D are the outputs. 8 input combinations, 8 output combinations corresponding to each of the inputs. Tabulate the programmable array logic programming table for the circuit. Mark the fuse map in a PAL diagram similar to the one shown in figure 7.17. Okay, here is the PAL programming table. Sum of product terms. What are the product terms? We have to find that out before writing the table. So from the truth table, use kmap and minimize it. You will get, if you minimize using kmaps, you'll end up with A is xz bar plus yz bar plus x bar y bar z. So here we'll write the product term x bar y bar z xz bar yz bar. Here we write the input x, y, z. Here we write the output. Before doing that, we really need to, before writing down the terms, we really need to find ABCD minimized form x bar z plus yz plus y bar z bar. C is a plus xy, so it's xz bar plus yz bar plus x bar y bar z plus xyz. So an extra term xy is present, and D is z plus x bar y. So in the inputs you'll have to include a also. That will make it easier. That will make the circuit simpler. For the output, A is x bar y bar z plus xz bar plus yz bar. We don't really need to write the product terms. We call them term 1, 2, 3. That's for A, x bar y bar z bar. We don't need A. Yeah, xz bar, yz bar. Then three more terms. Now for B, B is x bar z plus yz plus y bar z bar. We have x bar z plus yz plus y bar z bar. Three terms. So three terms in the sense you can have up to three product terms. You're provided three AND gates for each of the output function and one OR gate. So each of the, you can have three product terms and then OR them together. But you don't need three product terms for C because C is simply a plus xy. So you can just take a and xy, and D is just z plus x bar y. So you can just take z x bar y. Need only two AND gates for D also. Now you need the fuse map. It's nothing but this. You have the complemented and uncomplemented form of your inputs running as lines that you can connect to. So what one way of doing this is, initially they give you a circuit, a board with all these wired connections, and there's a connection product 1. This is an AND gate and an OR gate giving you A. From that you can give A here and A bar here. So they give you connections everywhere, all these places. Then you find out the product term that you want. Let's say you want the product term X bar, Y bar, Z. Then you keep only those connections to X bar, Y bar and Z and blow the fuses. There will be fuses for these connections. Blow the fuses to all other connections that you don't want. So you keep only these connections X bar, Y bar, Z and blow the fuse on the rest of them. So you'll get the term X bar, Y bar, Z. Then for the second product term, XZ bar. So here what it means, what this cross means is this: fuse is intact. If you don't have the cross, if you just have wires crossing each other, that means the fuse is blown. So here the fuse is blown. YZ bar. And X and X bar you give for the second term. Again you have 3 AND gates followed by an OR gate. So here there's no programming with respect to the OR gates. Only you only get to program the AND gates. You only get to program what product terms you get. Alright, we have two more functions C and D, but both of these only use one AND gate. So fuse is blown here, so that AND gate output is not taken. You just take A and XY. Finally, D, again one AND gate is unused. Simply has Z plus X bar Y. Again on this side also you write what are the inputs, what are those lines. X means fuse blown. A simple cross connection means fuse intact. Sorry, it's the opposite. Fuse intact, fuse blown. That's it. That's the fuse diagram of the PAL and the PAL programming table. Okay, that's it for today's session. We covered 7 chapters in the digital design textbook by Maurice Mano and Michael DiCiletti. We couldn't solve all the problems in those 7 chapters, but we tried to solve as many as we could. Alright, that's it. I hope you find the lectures. I hope you found the lecture series useful. Bye. See you in some other course, maybe.